Hello guys, welcome back to lecture series on linear differential equation with a constant coefficient, which is from M3 subject. For similar videos, check in my playlist. So in my today's video, I'm gonna explain to you all how can we solve Cauchy homogeneous linear differential equation or similar type of the example. Okay, whenever example in the form of Cauchy homogeneous linear differential equation. Okay, in such a case, how can we solve that linear differential equation? So I will explain to you all in our today's lecture. So stick to our today's lecture and let us see how the how this method it is easier. Okay, yes. Okay, now first of all, let me explain here how the Cauchy homogeneous linear differential equation look like. Okay, the differential equation. Okay, the differential equation the differential equation of the form a naught x raised to n d raised to n x by dx raised to n plus a1 x raised to n minus 1 d raised to n minus 1 x by dx raised to n minus 1, okay, plus an minus 1 x dy by dx an minus 1 x, okay, because n we end here with n minus 1, n as a 0, okay. So x dy by dx plus an into y, okay. So entire term I consider here as a f of x, okay. I consider this entire term as a f of x, like it is nth order linear differential equation, okay, with some constant coefficient. So we called this equation, okay, this differential equation we called as, this linear differential equation we called as Cauchy's homogeneous linear differential equation. Okay, what we call this one? Cauchy's homogeneous linear differential equation, okay. We call this one as Cauchy homogeneous linear differential equation. So in our today's video, I'm gonna explain to you all how can we solve the particular integral or the solution for Cauchy's homogeneous linear differential equation, okay. Now see that I will explain to you all the method here further, okay. So you must be very much careful because these steps are very important for solving the examples, and this method is also important, okay. Yes. So we can reduce this linear differential equation, okay, we can reduce this linear differential equation with a constant coefficient by substituting some of the values, okay. Let's reduce by using some of the values, okay. Let's reduce about linear differential equation by putting values, by putting some of the values, okay. Now which values we are going to replace here? Now see that as we have function in the form of x here, okay, so directly replace x, okay. So but what we are going to replace x, we want our differential equation in the form of exponential term, okay. Then it is easier to deal the values, okay, logarithmic or exponential. Whenever you have logarithmic or exponential term here present in our f of x, then it is easier to find out the solution, okay. So I'm going to replace that x as exponential term e raised to z, okay. I replace x as e raised to z, okay. Or if you do want the logarithmic term, take log from both sides. So log of x can be written as log of e to the power z, and log and e can be cancelled, then we left here with the value z, okay. Log x is equal to e to the power z, that means log of x which is equal to z, I applied log to the both side, okay. Log of x which is equal to z here, okay. And as we know that d by dz, okay, as we have term in the form of d by dz, okay, as we have term in the form of a z, then we replace d by dz as a capital D, okay, d by dz as a capital D. Till now we replace d by dx as a capital D, but instead of that we are going to replace log of z, okay. As we have log of x which is equal to z, so we are going to replace d by dz as a d, so term it is in the form of a z here, okay. Yes. So what we have here, we have the differentiation dy by dx, okay, independent dependent term here y and x, okay, dy by dx. So we are going to introduce z. We are going to introduce z here in the dy by dx. That means we have to differentiate y with respect to z, okay. So how we are going to replace dy by dz, okay. We are going to differentiate y with respect to z, but differentiation, complete differentiation with respect to x here. So by using chain rule, I am going to write dx by dz by dx, okay. That means I differentiate y with respect to z, and again z that differentiation with respect to x, okay. So dy by dx I written as dy by dz into dz by dx, okay. This one is a dz by dx, okay. Yes. So what we can write here, when z is log x, then dz by dx can be written as log x having differentiation 1 upon x, okay. I written this term using above step, okay. If z which is equal to log x, then dz by dx can be written as 1 upon x, okay. Yes. So dz by dx, replace it here. So I'm going to write dy by dx which is equal to dz by dx which is 1 upon x dy by dz here, okay. So what I have done, I replace only dz by dx as a 1 upon x here, okay. Yes. So 1 upon x dy by dz, okay. This one is the value for dy by dx here, okay. Yes, we are trying to reduce our Cauchy linear differential equation, okay. Cauchy linear differential equation into its a solution, okay, using substitution of some substitution method, okay. Yes. So take that x here to the other side of how we write x into dy by dx, okay. X into dy by dx can be written as dy by dz, okay. What I have done, I taken that denominator x to the other side. So I got the term x into dy by dx which is equal to dy by dz, okay. Yes, and d by dz we are replacing value as a d, okay. D by dz we replacing as a d and y as it is here, okay. So whenever we have x into dy by dx term, so you have to replace capital D into y, okay. This step you have to replace. But what happen if we have higher derivative like d square y by dx square, d cube y by dx cube? In such a condition, what we do? Now observe here, okay. I will explain to you all how can we reduce higher order differentiation over here, okay. Yes. So what we do? We want the double differentiation. That means d square y by dx square, okay. So we want the d square y by dx square, okay. D square y by higher order differentiation we are learning here, okay. Linear differential equation. So d square y by dx square, that means I'm going to write d by dx as a dy by dx, okay. That means d by dx as a dy by dx means d square y by dx square here, okay. Yes, d by dx, take it out here. What is the value for dy by dx? 1 upon x dy by dz, okay. Replace this value here, 1 upon x dy by dz here, okay. 1 upon x dy by dz. As we can see that this one is a two different function. 1 upon x is one of the function and dy by dz is another function, okay. So to solve the differentiation for these two functions, we apply directly product rule, okay. So differentiate by using product rule. First function as it is 1 upon x as it is, differentiation of dy by dz with respect to d by dx, okay. So dy by dz, we have to differentiate dy by dz, okay, with respect to, okay, so d by dx. So we are going to replace, okay, we are going to differentiate with respect to x over here. Next step here, 1 upon x as it is, d by dx of dy by dz, okay, plus I am applying only the by part rule, okay. First step as it differentiation of second plus second step as it is dy by dz as it is d by dx of 1 upon x, and we know that 1 upon x having differentiation minus 1 upon x square, okay. This one is the differentiation. Now we have to work on this step, okay. Be careful here with this step, don't get confused. 1 upon x d by dx of a dy by dz. So we have to differentiate dy by dz with respect to d by dx, okay. So how the differentiation it is coming? So 1 upon x keep as it is, okay. As we have function with respect to z now, first of all differentiate with respect to z and differentiate z with respect to that x, okay. Yes, then how we will get d by dx of a dy by dz, okay. D by dx of a dy by dz. So next step, we are differentiating with respect to x, okay. So d square y by dz square. So we are write d square, the differentiation here dy by dz, we are differentiating with respect to x, okay. So we take double differentiation over here, d square y by d square z, okay. So we are differentiating this term yet another time with respect to z, that z has to be differentiable with respect to x. Okay, then we write the dz by dx here. Okay, d square y by dz square d square z into d by dx. I'm differentiating with respect to x. Okay, yes, then z differentiate with respect to x. Okay, I hope you all have understood from this step to this step. It's quite confusing but not difficult. Okay, let me explain one more time. So what we do, we differentiate that term with respect to x, that means d square y by dz square, but we are going to differentiate using chain rule, that z with respect to x here. Okay, yes, and minus 1 upon x square. Okay, we write minus 1 upon x square dz by dy by dz. Okay, dy by dz. This step I reduce here in this form. Okay, yes, this one is the reduced form for this differential equation. Okay, so d square y by dz square can be written in this form. Okay, so what we do in our next step, so 1 upon x, it is out here. Okay, that 1 upon x and dz by dx, we know that dz by dx which is 1 upon x. Okay, that replace 1 upon x, this one is 1 upon x, so d square y by dz square into again 1 upon x minus 1 upon x square dz by dy by dz, sorry, it is a dy by dz. Okay, that is 1 upon x square, 1 upon x square take outside, so 1 upon x square, that means 1 upon x into 1 upon x. Okay, which is 1 upon x square. Again this 1 upon x square, take it outside, under bracket we left here with these two terms only. Okay, yeah, so d square y by dz square minus dy by dz. Okay, into d square y by, which is equal to d square y by dz square. Take x square to the other side, we get the x square d square y by dz square, which is equal to d square y, that means we dy dz I'm going to replace as a capital D. Okay, as a second derivative, take it the d square minus dy. Okay, so this one is our given reduced form. Okay, that means I'm going to write a d square minus d into y can be written as x square into d square y by dz square. Okay, so take some values, adjust it here, you will get this step. Okay, so we have to follow same condition in our examples. Okay, we have to apply same conditions in our example. Okay, so as we have d square minus d, okay, d square minus d into y, which is equal to x square into d square y by dz square. Okay, so how can we write the next step over here? Take that d common from here, then we write a next step x square, okay, d square y by, I'm writing here. Okay, next step after this, x square d square y by dz square. Okay, take d common from here, which is equal to d into under bracket d minus, okay, d minus 1 into y. Okay, so I'm going to take d common from here, so, and y common from here, y out here means d square minus d. Okay, d square minus d, take d common from here, d minus 1 it left here. Okay, yes, this one is the next step. So whenever we have x square d square y by dz square, we replace d into d minus 1 into y. Okay, so what we replace, whenever we have x square d square y by dz square, okay, we replace d into d minus 1 into y over here. Okay, yes, so similarly I'm going to write here x cube d cube y by dz cube. Okay, that means d into d minus 1 into d minus 2 into y. Okay, so what I have done, I just taken cube. Okay, that means I extended this step, generalized this step here. Okay, x cube d cube y by dz cube, d into d minus 1, as I extended one differentiation, that means obviously d minus 2 it is coming here. Okay, consider it logically, or you're going to solve the third order differentiation, you will get this step. Okay, so similarly we can write x raised to 4 d raised 4 y by dz raised to 4 can be written as d into d minus 1 d minus 2 d minus 3 into y. Okay, this one is a fourth power. How can we reduce the fourth power? Now see that, so when we have third power, which is a d into d minus 1 into d minus 2, then fourth power increase d minus 3. Okay, so when you have fifth power, increase d minus 4, sixth power d minus 5. Okay, in this form you have to expand these values. Okay, these are the actual value we wanted for our substitution. Okay, okay, so you will get this by using this, the solution for Cauchy homogeneous linear differential equation. Okay, so see that this one is our entire process for finding the Cauchy homogeneous linear differential equation. I hope you all have understood how to solve Cauchy's homogeneous linear differential equation. So in our next lecture we go for solving some of the example using Cauchy's homogeneous linear differential equation. Then concept will be very much clear for you all. Okay, now this is quite descriptive part, may be confusing to you all. Okay, but don't worry about it, we go for some of the example, then it will be very much clear for you all. Okay, so that is for our today's lecture. I explained here how to solve Cauchy homogeneous linear differential equation in our today's lecture, okay, using substitution. So I hope you all have understood. Even after, if you found anything difficult now, let me know in my comment section. I will come up with the similar videos. So thank you everyone. Thank you for my today's lecture.